Hello and welcome to this AQA Further Math Statistics video, the fourth in the series Discrete Random Variables 1, looking at the mean and variance of the uniform distribution. So a little reminder of a probability distribution you have met before, the score on an unbiased six-sided die where we can have the outcomes 1, 2, 3, 4, 5 or 6 and they are equally likely, so each has probability 1/6. And this is a discrete uniform probability distribution, and we can write in a more formal way this probability distribution by indicating that the probability that the score takes any particular value equals 1/6 for values of x that are integers, because it's a discrete distribution, between 1 and 6, and the probability of getting any other outcome is 0. So you'll quite frequently see these brackets and 0 otherwise appearing. So any standard discrete uniform distribution will take the discrete integer values 1, 2, 3 up to a particular maximum n. And that can be summarized as in this table here, and because n is the highest value that we can possibly get, that means we have n distinct discrete outcomes, and therefore the probability of each outcome is equal to 1/n. And that can be summarized again more formally by writing the probability that x, our random variable, takes any particular value little x is 1/n for x taking an integer value between 1 and n, and the probability is 0 for any other value for x. So if we just have a look at our discrete uniform distribution, so we don't know the value of n, but we do know the probability for each outcome is 1/n. And then if we want to look at getting a generalized result for the mean and the variance for a discrete uniform distribution with a range of outcomes 1 to n, then we're going to have to look at x multiplied by the probability and x squared multiplied by the probability. So we're going to need to consider, I won't put them all in, these outcomes, and we're going to need to sum those in order to get a general expression for the mean and for the variance. And here they are, all written out for you. So you might like to just spend a moment and jot that down. So if first of all we look at how we could get the mean mu, or the expected value, if you recall from the previous video, is the sum of each particular outcome multiplied by the probability of getting it. And that's simply that second row summed. And you're going to need to be familiar with sums of fairly simple series in order to get a nice neat expression for the general expected value for any discrete distribution. So if we look at simplifying that a little bit, this is what I wrote on the previous slide. If we take out 1/n, because n is a denominator for all these terms here, we then simply have the sum of the first n integers inside these brackets, and you should be familiar with the fact that the sum of the first n integers is a half multiplied by n multiplied by n plus 1, and then we can cancel the two n's and we're left with our result here in blue for the mean, or the expected value, for a general discrete uniform distribution where x takes the values 1 to n. If we now look at doing the variance, remember for the variance we need ex squared, so this second row here now has got x squared multiplied by the probability, which is what we need to use, and sum to get ex squared. And remember that we do need to subtract the mean squared as well. So for the variance, we're going to be looking at summing those values and remembering that we must subtract the mean squared. So obviously we need to focus on this and try and simplify that to get a general expression for the variance for x, where x follows a discrete uniform distribution. And here you can see it written out in a little bit more detail. And again, we can take, because n is a denominator for all of those items in this summation, we can take 1 over n out as a factor, and we are left here in brackets with the sum of the squares of the first n integers. And then just on the right hand side here, we have a half n plus 1 squared. A half squared will give us a quarter, and n plus 1 squared will just give us n plus 1 squared. So how can we simplify the sum of the first n squares? Well, hopefully you recognize this expression here as the formula for the sum of the first n integers, 1/6 n multiplied by n plus 1 multiplied by 2n plus 1. And what we need to do is to look at this row here and think what we can do to simplify it. So first of all, notice we have a 6 on the denominator there and a 4 there. So if we put them over a common denominator, 1/6 will give us 2 over 12, and 1/4 will give us 3 over 12. And here we can cancel the n. So we're left with 2 over 12, n plus 1, 2n plus 1, minus 3 over 12, n plus 1 squared. We then clearly have a factor of n plus 1 that we can take out. And then what are we left with? Well, if we take the 1/12 out, we're left with a 2 and 2n plus 1, that's here. And we're left with a 3 and another n plus 1 here. And if you just write that out, you'll find it's 4n plus 2 minus 3n minus 3. That gives us n minus 1. So we now have a much simpler expression, a general expression for the variance for a discrete uniform distribution. And we can simplify it even further to this expression in blue. So to summarize, for a discrete uniform distribution, the mean is a half n plus 1, and the variance is given by 1/12 n squared minus 1. And it's perfectly okay, unless you're asked to show or prove in an exam, if you come across a discrete uniform distribution and need to find the mean and variance, you can just use those standard results and quote them. So if we just look at a very simple little example here, we have an 8-sided die here. So we'd be looking at a series of outcomes for x, 1, 2, 3, 4, 5, 6, 7, 8. So in this case, n would equal 8, and the probability for each outcome would obviously be 1/8. So if we look at those standard results for the mean is n plus 1, so 8 plus 1 over 2, which is 4.5. And the standard result for the variance, n squared minus 1, so that would be 64 minus 1, 63 over 12, or 5.25. And remember that the standard deviation is the square root of the variance, so that would give 2.29 to 3 significant figures. And that concludes this fourth in the series.